Okay, so let's begin this talk. This is called Close Enough. It's Streaming Algorithms for a World of Limitations. An alternate title for this could be how computer scientists, mathematicians, and a bunch of ingenuity conspire to make your lives easier and less expensive. So as a kind of motivating example, we are going to inhabit the role of someone doing analytical work at an electric car charging network. You are in charge of figuring out how the whole network is working. So you're going to have to answer a whole bunch of different arbitrary queries. There's a bug in your software that means that some of your stations are sending high volumes of data at somewhat unpredictable intervals. Other people are working on that right now. They'll fix it. But you have to figure out a bunch of other questions about how it's working. This gives you a situation where you have lots of data. This is not unique anymore. It's not 2014. We're not bragging on how much data we have. If you're in connected cars, Internet of Things, monitoring analytics, or cybersecurity, you have probably more data than you can know what to do with. Quick aside, cybersecurity, I work for a company called Distill Networks. We protect your website from bots. I'm part of a team that is the bot detection efficacy team. We try to find out how to do a better job of finding bots and making sure that we block them for you. Our team is interdisciplinary. There are 3 of us data scientists, a computer scientist, and a traditional Swedish hacker, which is a lovely thing. You should get at least 2 or 3 of those on every team. One of the common things in all these high data volume situations is that memory and compute are often limited. If you're doing computing on the edge, on smartphones, in cluster computing, on connected cars, whatever it is, often you have some kind of fixed amount of memory and computation you can use because these are basically equivalent to money. So if you can reduce your total memory and computation budget, you can make the things you do cheaper. So can you do your work more cheaply is essentially one of the questions. In order to do that, often we approximate. So you can switch out your Fourier transforms for fast Fourier transforms. There are many different approximation algorithms to exact solutions, which is frequently a way to turn something from something which would only work if you had less than 10,000 rows to something that will work on tens of millions or higher. But we also do sneaky approximations, like we download a small enough data that's going to fit in RAM on your laptop, or you only limit an analysis to a particular client or a particular type of car. And those are ways where we are introducing bias in the sampling that we do. So what we're going to talk about here is a different way of doing it. There's the approximation that goes into it, but there's the streaming context is kind of its own thing. The other thing is, at a philosophical level, if your data is skewed and you have many more records that are high volume than small, effectively you're spending a lot more time and energy and computational resources and RAM on those heavy hitters. And it doesn't seem fair to the other data rows in your data sets. So we're going to talk about streaming algorithms to 3 major problems: count distinct, approximate counting, and percentiles. So we'll talk about a couple things before we get to the actual algorithms. The streaming formulation kind of arose in the late 70s, didn't really get formalized until in the 80s or 90s, and got a lot of attention in the 2000s. But basically, there are contexts where you don't get to keep all the data. And you have to make do with doing the best you can with the data as it comes through. The motivation people usually talked about was routers or sensor networks. For like the core infrastructure of the internet, they don't really get the ability to store all of the requests that come through. They need the ability to process them quickly and get close enough results. But also, unlike in a batch system where you know if you're going to start analysis of 10 million rows, then you know when you get to near the end that you're near the end and you don't have to worry about allocating a bunch more memory for things, which makes your life easier in some ways. In streaming, you process the data in the order it's received. You only get a single pass. You don't get to hold the data. So you're limiting yourself. But in real life, most systems that are actually running continuously are in a streaming unbounded context. If you're running a website, you don't really know exactly how many people you're going to have. You can have an estimate on it, but it could potentially spike with a DDoS or something and go vastly higher. So by limiting yourself to these fixed memory budgets, it's a good practice, and it ends up making some things kind of neat. Calculating the streaming maximum, for example, is trivial. For every record, you see what the highest value is, and if the new thing is higher than your old thing, you keep that. And then at the end, you have your highest value you saw in your data set. That's exact. That's great. Well, you can do a streaming average too. You store the number of items you've seen, and you store the total sum of everything you've seen. And then at any point, you can turn your two estimates into your estimate of your average, which in that case, you store two numbers and you've got an exact answer. That's great. But most streaming algorithms will make use of what is called a sketch. And in these, you calculate some dimensionality reduction that's purpose-focused for your data. So it's a small representation of your data that can answer the kind of limited scope of questions that it was designed to answer and very little else. If, for example, you have a database and you have a table where you aggregate the car and the number of location check-ins per car, you can answer questions about those components quite easily, but you can't answer questions about when they checked in. Like the specific minute, for example. You've lossily compressed your data, and it made it easier to do some things and impossible to do others. That's generally the idea behind a sketch, is you make it so you can just add water to get your estimate that you're looking for. You probably know what hashes are, but as a quick refresher, it's a way of distributing something evenly across a fixed number of buckets. A good hash doesn't take the content that you start with and encode it in similar regions. You don't want to have George Washington uppercase and lowercase right next to each other, because then it's kind of summarized your text. And you'd prefer for it to have no idea what that is, so that no matter what comes in, you get an even smooth output. They underlie almost everything about computation. They're super cool, and I have a data scientist colleague who he has his little idea. He has a whole book on hashes he wants to write. We'll see if he ever does. So the first problem is the approximate count distinct problem, which is estimating cardinality. And this is actually the reason I got into understanding this, is because there was a system at my work, Distill, where we were using hyperlog to do the estimation of the number of distinct items. And the more I learned about it, the more I tried to figure out how it even worked, because in general, if you want to know how many distinct things happen, the way you do that is you go through and you use some kind of a hash map or dictionary. So if I want to know how many distinct words are in this snippet of the Jabberwocky poem by Lewis Carroll, then we have a dictionary. We start with a counter that equals 0. Then we go through each one of these elements and we check to see if it was in the dictionary. If it wasn't in there, we increase our counter and we put it in there. If it was in there already, we don't do anything. This is relatively fine. The downside is, if you have as many distinct items as you have records, then it does require you to store every single thing. And so your memory requirement is on the order of O(n). If you're seeing 10 billion things, that means you're going to have to store quite a few things. So there was a gentleman in 1978 at Bell Labs, Robert Morris, who was dealing with a situation where he wanted to know not the count distinct, not the number of unique things that happened, but just the total number of things across a bunch of different, nobody knows, he wasn't allowed to say what he was talking about, but he wanted to count things, many of them, with a fixed memory budget for each. And so he came up with this idea that, okay, if I wanted to, instead of getting the exact count, if I could relax into the world where I'm okay with an approximation of the count. If you think about a coin flip, every time you see an event, you flip a coin. If it's heads, you increment your counter up. If it's not heads, you don't. You just leave it alone. At the end, then you can multiply your counter that you've stored by 2, and that would be your estimate, given that heads is about half the time. That'd be an estimate of the number of things you saw. So that's an interesting way of doing it. The downside is there's only a limited amount that you can actually represent that way. If you can only store 255 bytes, then you can, or if your maximum value you can store is 255, you can really only get to 510, or whatever that 2 times 255 is. Yeah, 510. So if instead you flipped a biased coin, the total value you can represent goes higher, but your variance also goes higher. So his third idea was to, instead of storing coin flipping kind of transformation, to store the log of the data that he was looking at, and then have a similar method to flip a coin and increment, and then only store the logs. This way you're storing a vastly reduced value relative to what you can estimate. That idea was interesting. And there's a gentleman named Philippe Flageolet, who was a French mathematician, computer scientist, and he really liked the Morris paper. In the mid-'80s, he wrote a big treatment of some of the mathematical characterizations, and one of them was that it required log bits to the amount of counters the Morris algorithm did. And so Flageolet thought, is it possible to do that for the approximate count distinct problem? And he came up with something which is clever. You start out with an estimation array of a number of zeros, and then you use the properties of a hash. We'll get to what exactly it's doing in a sec. You hash it, you find the leftmost one in the binary representation, which is the most significant bit. You set the array value to that most significant bit, and then you can use that number to estimate the cardinality of the data set. In general, you also need to average it by doing it either multiple runs, or you hash the data set into a couple buckets, and then you use the estimate from each of those buckets to reduce the variance of your final estimate. But the nice thing is, instead of needing ON memory, you need the number of groups times the number of hash bits you're storing. So it's fixed and vastly reduced. But actually, it's nice. We're back in coin flipping land. It's just that the hash distributed into a number, which is a series of zeros and ones, and you view the number of values before you get to your leftmost one as basically the number of tails before you hit a heads. And then you can use the probability of getting 3 tails and then a heads. You can say, well, if it would have taken 1 of every 16 times to get that result, then you can estimate that probably you saw about 16 things. So you're hashing it. You're taking the properties of the hash to find how unusual an occurrence is the most unusual occurrence in your data set, and then you're using that to infer how big was your data set. There have been some optimizations to it over the years. He created a even lower memory budget version called superlog, and then he changed out the geometric mean for a harmonic mean, and that was hyperlog. You might have heard of hyperlog. Google really loves it. They use it for their search results and a lot of estimated count distincts across their whole suite of products. In fact, they spent 6 months or however much time they did and several engineers worth of effort to figure out ways to get hyperlog to be more accurate, especially on lower cardinality values. And they came up with what they call hyperlog++. Instead of using 32-bit registers, it uses 64 bits, and it has some correcting functions for some of the lower estimates. But basically, anytime, if you were thinking of aggregating on the model of cars for your connected car network that you're trying to analyze to see car charging, if you were to do select count distinct from a table grouped by something, then you would need your aggregation key order. You'd need your number of aggregation keys times your number of records, total memory space, to do that aggregation. But if instead you use hyperlog, it's going to be that aggregation keys times log n. So it's a much smaller amount. We use this in feature calculation, both in our edge computing environments, but also when we do our big computations in Presto. And it's incredibly helpful. The error bounds on hyperlog are something like 2%. And it, in practice, it's super fun. If you wanted to go out and start using hyperlog, if you're using Impala or Spark or Vertica, Azure SQL, Oracle, they all have some version of this approximate count distinct. And if you're using Presto, Druid, Accumulo, or Redis, they not only have the approximate count distinct, but they have that sketch, the intermediate representation, so that you can calculate aggregates at a per day level and then merge them if you're going to do an aggregate at a per month level. So you can reuse those calculations. Any questions about that before we're done with approximate count distinct? OK. So the next problem is approximate counts. Counting things we all feel like we have a fairly good handle on. It's in data science, it's one of those things, it's like the hello world. For every event you look through, you increment the counter up if it's in there already. If it isn't in there already, you just add it and set it equal to 1. And you could need as much memory requirement as its ON also. So let's build ourselves an approximate counter. So we pick a fixed number of buckets and we hash into those buckets. So we're evenly distributed among those buckets. Then for everything we see, so every license plate for a car that we're seeing, we hash that value, and then we increment the bucket that it was hashed into by 1. At the end of that, we have an array of values representing the counts of where things were hashed into. And then we can use that to calculate how many, if you want to know for a particular value, you hash that value, figure out what was in the bucket, and see what the count is. In this way, you have a fixed array representing, it gives you an approximate version of the counts for the entire data set. But the wheels in your brains are turning, and you already know the problem with this. As formulated, what is terrible about this algorithm? Hash collisions. If you're trying to take 10 billion things and fit them into 100,000 slots, you're going to get things that end up in the same spot. So in order to mitigate that, if we, instead of doing it one time with a single hash function, we take a bunch of hash functions, and then we have a table that's the size of the number of buckets that we decided we were going to keep and the number of hash functions, then for everything we see, we hash it. We have each hash function hash it into the bucket and increment the counter associated with that. Then the probability of getting a hash collision is not the probability of two things ending up in the same bucket from one hash function. It's two things ending up in the same bucket from every hash function, which is vastly lower. This actually has trade-offs. You can use your number of buckets and your number of hashes to pick your desired error percentage. The interesting thing is, so what's the most collision-resistant way to estimate the counter from this data structure? If I went through iHash and it turns out that the estimates from the 3 rows are 1, 6, and 3, how do I figure out what the best estimate for the total number of times we saw an event is? Given that hash collisions are going to result in two things incrementing the count up at the same time, the most collision-resistant thing is the lowest value. So you take the minimum count of any of these, and that is the count min sketch. So you have m hash functions, d buckets, and you hash into the buckets, and then you find the lowest estimated count for your item. I think it's so elegant and cool. It also has the benefit that you can do other things with it. So if you have a heap that stores the top 20 values, as you're going through your data set, every time you update the count of something, you can put it into your heap and see if it belongs in that sorted tree. And if it belongs in the heap, then it'll stay in there and dislodge the lowest thing that's already in there, which means that as you are running this data structure with the heap on the side, you have a running counter of the top most frequent elements, approximately. It's the approximate count for each of the approximate top most elements. But in this way, if you allocate a certain size for your count min sketch and a certain size for your heap, then you have basically a fixed memory budget version of your top most frequent values. And if you relax your streaming situation and you're allowed to look at your data again, if you, instead of increasing the count every time, you decrease the count every time after some fixed time window, then your estimate in your count min sketch at any given time is only the values that are within that time window. So then you have a windowed approximate counter for that relevant time period you care about. The people who made the Countman sketch, they built a website. They also did another paper in early 2011 or late 2011 that is their kind of soft, gentle introduction to the paper. They're both really eminently readable and interesting, and have some other cool applications. Any questions on this one? OK. Third problem we're going to talk about is quantiles. We know what quantiles are. If you've ever seen growth charts, that's percentiles. Quantiles are just, doesn't have to be divisible by 100. If you want to estimate the quantiles for a data set, as a statistician, I think ethically obligated to tell you that if you know it's normally distributed, you only need two numbers, the mean and the standard deviation, then you can summarize the entire data set. But since most of the time you don't know the distribution, the quantile digest is a great way to do that. And the way it works is you store a binary tree that has a leaf for every point in your data set, and then you compress the tree as you go along. And every time you compress the tree, it becomes slightly less accurate, but also it keeps the values you're looking for. So yeah, you store a binary tree with a leaf for every value. So then what the saying here is, we've seen, according to this, nothing in the 1 and 2 buckets. There's 4 in the 3 bucket, 6 in the 4 bucket. And when you read this, we know that this means that either of these values, there's 2 of them. When you compress the structure, there's these 2 rules. The count for a particular node has to be less than the floor of n over k. The k is the compression parameter, n is the total number of records you've seen. So it has to be less than n over k. And also, you want the node and its parent and its sibling to be greater than that floor value. Essentially, it's saying you don't want a bunch of really small values. You want to merge things together to larger clusters. And so these 3 compress up to this value here. These ones move over. They move up the tree. This moves up to the top. And every time you do the compression, you lose a little bit. But at the end, you're summarizing the data set in 5 data points, where originally it was 7. It is, to query it, you go from the smallest to the largest and create essentially this list of the vertexes and the counts. And then if you wanted to find out what the quantile was, what the value is for a certain quantile. So if we pick our quantile as 0.6, so what 60% of the data is at this level or low, you add up these vertices until they exceed that number. So the total number of elements was 15 times 0.6 equals 9. We've got the 4 here and the 6 here. Add those up and we're over 10. So this is our estimate. So we'd say that our estimate is at that the count equals 4. Or yeah, I say 6. It's 4. The nice thing about the quantile digest is you can also do inverse percentile or quantile questions, which is how much of the data is above some threshold. And then because you can do that, you can do 2 of those and say how much is above this threshold, how much is above this threshold, and then you have the range for in between them. And you can also figure out how many values had more than a certain threshold. So you can do frequent item sets, which you can use, again, to get another version of like an approximate top values. Pick a threshold, see if they're there. And this is all a reduced memory structure. It's kind of neat because then you can summarize the whole distribution in this like smaller data set. But there's a question. The quantile digest gives us a same relative error percentage across the whole data set. But is that really what we want? Does knowing that the 0.99 and 0.99th percentile and the 0.49 and 0.499 percentile, should those really be the same? Do we care as much about that? Or do we typically care more about those extreme percentiles? I think most of the time we care more about the extremes. So there's a different data structure. A gentleman named Ted Dunning, really clever thing, basically used k-means to cluster your one-dimensional data distribution and keep the centroids, the location of the points that you're storing, and the number of records that are within each point. And then you have a way of summarizing the distribution. And you pick a distance metric that allows you to usually keep your small clusters around and merge your big clusters together. So it's kind of the opposite of the quantile digest in that way. So with a t-digest, the graph on the right shows where the records are, where the centroids are. And as you can see, the places that have larger changes have more centroids, and the place where there are few, there's gaps, because the total data distribution isn't changing much there, so we don't need to dedicate as much of our compression to it. In general, t-digest outperforms q-digest for everything except central tendency measures. Like your median's going to have more error on the t-digest, but those edge distributions are going to be much tighter. Question?
You go back to where you're talking about the t-digest one slide before there. What do you mean it's k-means-ish centroid? Like, so k-means typically you would say k is equal to 5, you pull the data points together. Does this, the way you're explaining it, made it sound like you would end up with more or less k's?
No, you get a fixed budget of k's.
Okay.
But how many? But the distance metric allows you to have it biased towards small clusters and merging large clusters, because you're also going to merge things that are close to each other within that distance metric. And so what you add new, and really effectively what you do is you have a cluster, you have a buffer, the points, and the merge space. You have your centroids, and when you see new data, you add them in, and then eventually say, all right, let's merge these and make sure we keep the number that we really need. So you allocate like more centroids and then fewer to keep it to the real thing. But yeah, and as he points out, this is his slide, completely static memory requirements. Both Q-digest and T-digest are mergeable, so they work for distributed and edge computing. And also, you can take aggregates and aggregate them at a higher level than you started with. And you can use them for kind of everything, wherever you want percentiles or data distributions. So at a high level, the summary is if you have a count distinct problem, you want to know the approximate counts, use hyperlog. If you want to know approximately how many things happened, use the count min sketch. If you want to know quantiles, probably you want the t-digest. And beyond that, there's been a ton of work in streaming algorithms and calculations for graph partitioning, for counting triangles. There's just been a whole host of research on this. And the reason I wanted to talk about this is because although I feel like data engineers know about this stuff, and there are certain subfields of the computer science and math stuff, most people who are trained in data analysis aren't learning about this stuff in their training. And I think it's tremendously useful for the work I do. And I think there's a lot of people for whom it would be also. Even if it's not what is considered cutting edge by the research community at this point. So I've got some links and resources. This is the biggest one. If you look up streaming links, there's this gist, which has a whole bunch of different things. Major blog posts about it, major presentations, summaries. There are a bunch of implementations. The Streamlib is a Java library that has a bunch of approximate algorithms on streams. There's the t-digest original implementation and a Python one. And then I showed you the list of all the ones, the databases that have approximate count distinct as built-in functionality. This is a bunch of courses from that list earlier. And then questions. OK. Well, that's all I have for this. If anybody wants to talk to me, I'll be here. Thank you for listening.